All right, everyone, we're going to cover our final topic here with intervals, and that's the prediction interval. So up until now, we've been constructing confidence intervals, and we've done that for all the different flavors out there. The mean of a single sample, the mean difference between paired samples, so kind of a before and after. And in that case, the confidence interval is based on the average of the differences in the before and after of those paired samples. And then we've also looked at the difference in means between two samples. So are the samples different enough to say that they're different? And that's an important distinction between the mean difference of paired samples and the difference in means. So make sure you go back and check that out, know the distinction there. And we spent a lot of time talking about what a confidence interval is, how to interpret it. So it's the upper and lower bounds, the interval that contains with a certain confidence or probability the true population parameter of interest, i.e. the population mean. So if we make a confidence interval for a sample mean, that interval with the, let's say 95% or 90% confidence, whatever you choose, will 90% of the time, say you take 100 sample means, 100 different samples, 95% of those intervals will contain the true population mean. All right, so a prediction interval is different. And what in this case, what if we're interested in understanding the certainty or probability related to a future single observation? What's the range that we expect to see that observation within, centered on the mean? So we can create an interval called a prediction interval that in which we can expect a single future observation to fall within with a certain probability. So that's what we're here to do today. Now, let's just look at a little theory here for the prediction interval. All right, so I've got my mean here, let's just say X bar, and then I've got a confidence interval that goes on either side of that X bar that we've calculated. Well, now, and what this, it's all based on the mean, and you're gonna have different X bars, different samples, different locations. In this case now, with the prediction interval, we're interested in finding an interval, and it's going to be wider. So I'm just going to draw it like this, still centered on X bar. But now I'm interested in this interval with a certain level of confidence that, let's say, a future observation X1 or X2 or X3 could fall within. And so when I think about a 95% prediction interval, then 95% of the time, future observations will fall within this interval. So 95% of future observations will fall in that interval. So that's what that's all about. All right. Let's look at a little bit of the theory here. So if I say X bar, really I'm thinking about the difference between X bar and some future observation. Let's call it X star. And what I'm talking about is that difference right here. So some future observation that's going to fall within this realm, this range, and then that difference is what we're thinking about here. So if we know X bar follows a normal distribution, now for this particular equation that we're using, we're saying X also follows a normal distribution. As we learned previously, the X bar based on the central limit theorem, sample means typically with large enough sample follow a normal distribution. But now we're imposing this requirement here that the sample itself comes from a normal distribution, all right? So if that's the case, then this difference will follow a normal distribution with a mean of 0, right? Because they could fall on either side of the X bar. So the mean of the difference should be 0 if we say do it 1,000 times. And then now we got to think about the linear combination of these two random variables. Well, the mean is how we described it here, but now the linear combination, when we think about combining random variables either with pluses or minuses, we always add the variance or add the standard deviation. So let's just look at it this way. So the variance of x bar is sigma over square root of n. That's the standard error. And then the variance of x, if it comes from that normal distribution, it's just going to be, sorry, I got these wrong here. This is standard error, standard deviation of x. Okay, so the variance is going to be sigma squared over n. And then the variance of x is going to be sigma squared. So we're adding those because in linear combination, you add the variability or add the variance. So a normal distribution with the following: sigma squared over n plus sigma squared. Okay, and if we factor the sigma squared out, we get 0 sigma squared times 1 plus 1 over n. All right, and this value right here for the variance is really the big difference here, the big kicker for why prediction intervals are so much wider than confidence intervals, because we're accounting not only for the variability or the variance in x bar, but of individual observations from the original population. All right, so let's just construct ourselves a or prediction interval based on that theory. All right, so for large samples, all right, n greater than 30, normally distributed sample. So the original population itself is normally distributed. And we know our population standard deviation. So if we're in this realm, then we can say the following. Our prediction interval is going to be x bar plus or minus z. We're going to use the z-score since it's normally distributed, alpha over 2. And remember, alpha is related to our confidence level. So our confidence level, let's say it's 95%, that is equal to 1 minus alpha. That's just how we just define alpha. And then alpha is equal to 0.05, alpha over 2.025, right? Okay, so z over alpha times sigma. We're saying we know the population standard deviation. Sorry, Zoom is really making it hard to write. And then times square root, 1 plus 1 over n. All right, so all we did was here we have the variance, here we have the standard deviation, all right? Just took the square root of it. So that's our prediction interval. And then if we want to do a small sample situation here, small sample, pi, then we're looking at x bar plus or minus t alpha over 2, okay, t for the small sample, and then our degrees of freedom n minus 1, and then we've got s instead of sigma times the square root of 1 plus 1 over n. So that is our small sample prediction interval. All right, so let's just apply this real quick with a tiny example. All right, and we're going to look at, let's make that a little bit bigger. We're going to look at the yield strength of steel welds. Okay, so we make these steel welds. Say we're the engineering club that's at the steel bridge competition today. And they did a bunch of steel welds, right, to make that bridge and make all those parts to put them together. So maybe they wanted to do a little experiment. They've got person A club member A, their treasurer, and they go out and do some welds, and then they got person B and they do a bunch of welds, and they want to test them. They put it in the shear machine or whatever it's called, and get the yield strength and KSI, kill a something per square inch. Kips per square inch. All right. So here's our sample. Y is equal to, and we've got 56.3, 65.4, 58.7, 70.1, and 63.9. Great. That's our sample. So we've got 5 of those. So n is equal to 5. And we'll go ahead and calculate y bar. That's going to be 62. We'll just say about 63. So 63, 62.88. And then the standard deviation of y is about 5.5. Great. So now let's create a 95% prediction interval. Okay, so someone is going to go out and test a random weld out there on the bridge, and they want to figure out what's this prediction interval within which that one random weld will fall. All right, so that's going to be y bar plus or minus, and we've got a small sample here, so we're going to use our nice t-score. Our degrees of freedom are n-1, so that's 4. Ooh, 4 degrees of freedom, and then alpha over 2 is 0.025. And then we're going to have s times the square root of 1 plus 1 over 5. Great. All right, so the only little task we have to do here is go find our t-score. So let's zoom over and go to our handy t-table here. Now this is just for alpha, which is on one side, but we want alpha over 2. We said alpha over 2 was 0.025. So let's use that. So we're going to be in this column. Tried to change the color there. And then our degrees of freedom was 4. So let's do that. Great. All right, so 2.776 is our t-score. And then we can write that out. All right, so that gives us 63 plus or minus 2.776 times 5.5 times 1 plus 1 over 5, 1.2. All right, so that gives us the following, and I'm going to write this out here. We'll do green for our confident or prediction interval. So here right in the middle, we've got 63, and then our prediction interval goes all the way out to plus or minus, looks like about 16 KSI. So that gives us about 52 over here. And that gives us about 86 over here. All right, so that's our prediction interval. And then if we're going to do our confidence interval, just to superimpose it and look at that and compare the two. So this is PI. Our CI looks like this. It's still centered on the mean, but it's going to be much more narrow, 56 to about 70. All right, and remember that's based on the fact that we don't have this 1 here, right? For the confidence interval, we get rid of that 1, and everything else is basically the same for the confidence interval. All right, so again, confidence interval with a certain level of probability that will overlap the true population mean. Okay, so let's just say the true population mean mu y is here. And the prediction interval, a little bit different interpretation. This is where some future value, y, we'll call it y star, would fall. It could be over here. It could be over here. It could be right here. And it's much wider because we have to account for the internal variability of the original sample distribution, which we said was normal. Okay, one more thing I wanted to put in here. And that is this. So let's just zoom in. So what this figure is showing you is kind of bringing everything together here. In light blue, we've got the original sample distribution, which we said was normal based on the prediction interval formula that we used. You can come up with prediction intervals for different distributions, but in this case, we're just going to say it's normal, keep it simple. Then if we take a sample of that, say n equals 8, take the mean, then here's the distribution of the sample means. It's much tighter. It's got a standard deviation of s divided by square root of n. All right. Now the vertical lines show, the dark blue ones are going to show us the confidence interval for the mean, so it's narrower. Light blue is the prediction interval for a future observation. And the reason I'm showing these two distributions is that you can see that based on the sample size, the prediction interval represents probability within the original sample distribution, or the original population distribution that we sampled from. Now, as n increases, the prediction interval is going to approach this value right here, which is 1.96 sigma or s, whatever we're dealing with. In that case, that's negative, and this would be positive 1.96. All right, and that represents, as we get larger and larger n values, that prediction interval shrinks, but it's not going to go beyond these values because ultimately this area right here between those two bars is 0.95% of the original sample distribution. So the highest confidence we can have, or the narrowest prediction interval we can have for a future observation, is really just that center 95% probability of the original sample distribution. So plus or minus 1.96 sigma. All right, that's what I wanted to talk about. Enjoy making those intervals out there, and we will continue this discussion with hypothesis testing. Bye.